Lithium batteries are disposable batteries that have lithium metal or lithium compounds as an anode. They stand apart from other batteries in their high charge density and high cost per unit. Depending on the design and chemical compounds used, lithium cells can produce voltages from 1.5 V to about 3.7 V. By comparison, lithium-ion batteries are rechargeable batteries in which lithium ions move between the anode and the cathode, using an intercalated lithium compound as the electrode material instead of the metallic lithium used in lithium batteries. Lithium batteries are widely used in products such as portable consumer electronic devices. History. Description. The term lithium battery refers to a family of different chemistries, comprising many types of cathodes and electrolytes. The battery requires from 0.15 to 0.3 kilograms of lithium per kWh. The most common type of lithium cell used in consumer applications uses metallic lithium as anode and manganese dioxide as cathode, with a salt of lithium dissolved in an organic solvent. Another type of lithium cell having a large energy density is the lithium-thienyl chloride cell. Invented by Adam Heller, lithium-thienyl chloride batteries are generally not sold to the consumer market, and find more use in commercial, industrial applications, or are installed into devices where the consumer does not replace them. The cell contains a liquid mixture of thienyl chloride and lithium tetrachloroaluminate, which act as the cathode and electrolyte, respectively. A porous carbon material serves as a cathode current collector which receives electrons from the external circuit. Lithium-thienyl chloride batteries are well suited to extremely low current applications where long life is necessary, such as wireless alarm systems. Chemistries. The liquid organic electrolyte is a solution of an ion-forming inorganic lithium compound in a mixture of a high permittivity solvent and a low viscosity solvent. Applications. Lithium batteries find application in many long-life, critical devices, such as pacemakers and other implantable electronic medical devices. These devices use specialized lithium iodide batteries designed to last 15 or more years. But for other, less critical applications such as in toys, the lithium battery may actually outlast the device. In such cases, an expensive lithium battery may not be cost-effective. Lithium batteries can be used in place of ordinary alkaline cells in many devices, such as clocks and cameras. Although they are more costly, lithium cells will provide much longer life, thereby minimizing battery replacement. However, attention must be given to the higher voltage developed by the lithium cells before using them as a drop-in replacement in devices that normally use ordinary zinc cells. Lithium batteries also prove valuable in oceanographic applications. While lithium battery packs are considerably more expensive than standard oceanographic packs, they hold up to 3 times the capacity of alkaline packs. The high cost of servicing remote oceanographic instrumentation often justifies this higher cost. Sizes and formats. Small lithium batteries are very commonly used in small, portable electronic devices, such as PDAs, watches, camcorders, digital cameras, thermometers, calculators, laptop BIOS, communication equipment and remote car locks. They are available in many shapes and sizes, with a common variety being the 3-volt coin-type manganese variety, typically 20 mm in diameter and 1.6–4 mm thick. The heavy electrical demands of many of these devices make lithium batteries a particularly attractive option. In particular, lithium batteries can easily support the brief, heavy current demands of devices such as digital cameras, and they maintain a higher voltage for a longer period than alkaline cells. Popularity. Lithium primary batteries account for 28% of all primary battery sales in Japan but only 1% of all battery sales in Switzerland. In the EU only 0.5% of all battery sales including secondary types are lithium primaries. Safety issues and regulation. The computer industry's drive to increase battery capacity can test the limits of sensitive components such as the membrane separator, a polyethylene or polypropylene film that is only 20 to 25 micrometers thick. The energy density of lithium batteries has more than doubled since they were introduced in 1991. When the battery is made to contain more material, the separator can undergo stress. Rapid discharge problems. Lithium batteries can provide extremely high currents and can discharge very rapidly when short-circuited. Although this is useful in applications where high currents are required, a too rapid discharge of a lithium battery can result in overheating of the battery, rupture, and even explosion. Lithium-Thienyl chloride batteries are particularly susceptible to this type of discharge. Consumer batteries usually incorporate overcurrent or thermal protection or vents to prevent explosion. Air travel. From January 1, 2013, much stricter regulations for the carriage of lithium batteries were introduced by IATA regarding the carriage of lithium batteries by air. They were adopted by the International Postal Union. However, some countries, e.g., the UK, have decided that they will not accept lithium batteries unless they are included with the equipment they power. Because of the above risks, shipping and carriage of lithium batteries is restricted in some situations, particularly transport of lithium batteries by air. The United States Transportation Security Administration announced restrictions effective January 1, 2008 on lithium batteries in checked and carry-on luggage. The rules forbid lithium batteries not installed in a device from checked luggage and restrict them in carry-on luggage by total lithium content. Australia Post prohibited transport of lithium batteries in airmail during 2010. UK regulations for the transport of lithium batteries were amended by the National Chemical Emergency Centre in 2009. In late 2009, at least some postal administrations restricted airmail shipping of lithium batteries, lithium-ion batteries and products containing these. Among these countries are Hong Kong, USA, and Japan. Methamphetamine labs. Unused lithium batteries provide a convenient source of lithium metal for use as a reducing agent in methamphetamine labs. Some jurisdictions have passed laws to restrict lithium battery sales or asked businesses to make voluntary restrictions in an attempt to help curb the creation of illegal meth labs. In 2004, Walmart stores were reported to limit the sale of disposable lithium batteries to 3 packages in Missouri and 4 packages in other states. Health issues on ingestion. Button cell batteries are attractive to small children and often ingested. In the past 20 years, although there has not been an increase in the total number of button cell batteries ingested in a year, researchers have noted a 6.7-fold increase in the risk that an ingestion would result in a moderate or major complication. The primary mechanism of injury with button battery ingestions is the generation of hydroxide ions, which cause severe chemical burns at the anode. This is an electrochemical effect of the intact battery, and does not require the casing to be breached or the contents released. Complications include esophageal strictures, tracheoesophageal fistulas, vocal cord paralysis, aortoesophageal fistulas, and death. The majority of ingestions are not witnessed. Presentations are non-specific. Battery voltage has increased. The 20 to 25 mm button battery size are more likely to become lodged at the cricopharyngeal junction, and severe tissue damage can occur within 2 hours. The 3V 20 mm CR2032 lithium battery has been implicated in many of the complications from button battery ingestions by children of less than 4 years of age. Button batteries can also cause significant necrotic injury when stuck in the nose or ears. Disposal. Regulations for disposal and recycling of batteries vary widely. Local governments may have additional requirements over those of national regulations. In the United States, One manufacturer of lithium-ion disulfide primary batteries advises that consumer quantities of used cells may be discarded in municipal waste, as the battery does not contain any substances controlled by U.S. federal regulations. Another manufacturer states that button-size lithium batteries contain perchlorate, which is regulated as a hazardous waste in California. Regulated quantities would not be found in typical consumer use of these cells, as lithium in used but non-working button cells is still likely to be in the cathode cup. It is possible to extract commercially useful quantities of the metal from such cells as well as the manganese dioxide and specialist plastics. From experiment, the usual failure mode is that they will read 3.2 V or above but be unable to generate useful current. Some also alloy the lithium with magnesium to cut costs, and these are particularly prone to the mentioned failure mode. Latest technology: Lithium-Air batteries. In November 2015, a team of University of Cambridge researchers furthered work on lithium-air batteries by developing a charging process capable of prolonging their battery life and battery efficiency. Their work resulted in a battery that delivered high energy densities, more than 90% efficiency, and could be recharged for up to 2,000 times. The lithium-air batteries are described as the ultimate batteries because they propose a high theoretical energy density of up to 10 times the energy offered by regular lithium-ion batteries. They were first developed in a research environment by Abraham and Jiang in 1996. The technology, however, as of November 2015, will not be immediately available in any industry, and it could take up to 10 years for lithium-air batteries to equip devices. The immediate challenge facing scientists involved in its invention is that the battery needs a special porous graphene electrode, among other chemical components, and a narrow voltage gap between charge and discharge to significantly increase efficiency.